I've started mine, so.
Within Barber County, Kansas. This research was conducted in Barber County, which is located in the red portion of south central Kansas, as indicated by the figure on the left. The property where this research was conducted is a privately owned ranch of 4,000 acres, indicated with the laser pointer and the black square on the figure on the right. I did have permission from the landowners to conduct this research on their property. Barber County, Kansas is known to have karst features. Some examples seen in Barber County are caves, sinkholes, springs, and swallow holes. This photo by Kathy Benison shows buttes and mesas that are commonly seen within Barber County. Kathy Benison is a prominent geologist who has done a lot of extensive research with the evaporites commonly seen in Barber County. At the time of this research, no method of karst feature prediction was available to the landowners. This photograph is from Google Earth, showing the 4,000 acre ranch where this research was conducted. Previous work by Caitlin Gavi, a previous master's student, suggested a petrographic control to karst feature formation within Barber County, Kansas. Looking at the geology of Kansas as a whole, this research was conducted in Barber County, which is indicated by the laser pointer, and the rocks here are Permian in age, which is signified by the blue in this statewide geologic map and also the geologic cross-section. Looking at Barber County specifically, the rocks within this study area are from the Nippawalla group, which is Permian in age and was formed around 279 million years ago. So what is karst? Karst is a landscape that is developed on soluble rocks. Some examples of karst features include caves, sinkholes, epikarst, and swallow holes. These are some caves commonly seen within Barber County. A cave is defined as a void large enough to admit a human. These caves are just big enough for me to crawl through to give you a sense of scale. These are some sinkholes commonly seen within Barber County. They can vary in depth. The photo on the left is a relatively shallow sinkhole. They can also become very deep, as indicated on the photo on the right. A sinkhole is defined as a depression caused by a collapse of the surface. Epikarst is also seen within the study area. Epikarst is defined as a solutionally enlarged opening or shallow superficial karst, and this is commonly seen within the research area. Swallow holes are also seen within this area. They can also vary in size, as indicated by these photographs. A swallow hole is defined as a visible opening that acts as an insurgence point for water to enter the subsurface through fractures and joints, as you can see by this middle photograph. So some brief background literature. Karst predictability models have been created in other regions, but not before in Barber County, Kansas. Multiple researchers have shown that if you combine multiple variables together, such as slope, aspect, elevation, the detailed geology, and other variables, it is an effective method of karst feature prediction. There have been other methods used to identify karst features from imagery, such as the sync fill function within ArcGIS, and also using orthoimagery and previous maps of the study area. 3 hypotheses were tested during this thesis. The first hypothesis was that a predictive model could be created to identify the location of karst features, and it would be more accurate than the sync fill function within ArcMap. The second hypothesis was that a higher amount of vegetation density according to the normalized difference vegetation index, or NDVI, signifies a greater amount of karst features present. The third hypothesis was that a single petrographically uniform layer controls the karst feature formation on this property. So why is this important? This is important for the prediction of karst feature locations. Vulnerability to, you can be vulnerable to infrastructure collapse or livestock loss if you're near karst features. If you know where the features are located, you can also protect sensitive ecosystems. You can also prevent and mitigate aquifer contamination. This is also important for understanding the mechanism of karst feature formation within Barber County and a broader understanding of karst in general. Multiple data sources were used during this research. The data sources included the United States Geological Survey, the United States Department of Agriculture, the Kansas Data Access Support Center, or DASC, and 50-centimeter QuickBird imagery of the study area was purchased from Digital Globe, which is a subsidiary of the company Maxar as of late last year. Data conditioning had to take place before the models were created. A file geodatabase was created to store the data files used in this research. The geographic coordinate system was also made consistent between all of the data sets used in these models, as well as the cartographic projection. This photograph on the bottom shows a snapshot of the file geodatabase where this data was stored. There is a lot more data within this geodatabase than what is shown in the photograph. Two models were created during this thesis. The first model was the non-normalized model. Within this model, the variables were equally weighted or all given the same weight. These variables and the model were not normalized or placed on a scale from 1 to 10. The second model that was created was the normalized and weighted model. This model is where variables were normalized or placed on a scale from 1 to 10. The variables were weighted more on a realistic basis. The geologic contact was given the highest weight out of all of the variables used in this model. When the non-normalized model was created, the raster calculator tool was used within ArcMap. The variables that were used within this model included elevation, slope, aspect, the normalized difference vegetation index, or NDVI, distance to roads, distance to hydrologic features, the land cover / land use, and the detailed geology. Looking at elevation, the hillshade, which is shown on this photograph on the right, was created from the LiDAR Digital Terrain Model, or DTM. This hillshade shows the elevation ranges for the study area used in this research. The ranges of elevation are from 500 to 700 meters in elevation, plus or minus 1 meter. The sink fill function was also used. This is a common method to identify enclosed basins, also called sinks, and is used with the sink fill function tool within ArcMap. When looking in karst areas, these are interpreted as sinkholes. This property had a large number of man-made ponds and retention basins, which were also identified with this function, which are these colorful features as seen on this figure on the right. Slope is defined as the measurement of the land gradient used for a certain area, and this is in degrees. This was created with the slope tool within ArcMap. This photo on the right shows the slope ranges within the property. The green areas are areas of low slope, and the yellow and reds are areas of high slope within the area. Aspect is measured in degrees from 0 to 360 and compass direction. This aspect shows the measurement that the slope faces. This was calculated from the slope output using the aspect tool within ArcMap. This photo on the right shows the aspect for the study area and is indicated by degrees and compass direction. The NDVI average was calculated from 7 months of data from the year 2018. The raster calculator was used to calculate the NDVI average. The red on this figure shows areas of higher NDVI, and the green shows areas of lower NDVI. The distance to roads, which is shown on this figure on the right, was calculated from the Euclidean distance tool within ArcMap. The shorter the distance to the road, the higher probability of karst feature expression. The distance to hydrologic features was also calculated from the Euclidean distance tool within ArcMap. It appears that karst is closer to the hydrologic feature within this study area as indicated by the figure on the right. The land cover / land use was sourced from the US Department of Agriculture. Within this study area, the land use classification of grass pasture is the most commonly seen in this property area. The land use classification of deciduous forest, which is the dark green areas within this property, is the second most commonly seen. The geology, the geologic contact was initially mapped by aerial imagery instead of field verification by the Kansas Geological Survey, or KGS. The contact between the Flower Pot Formation and the Blaine Formation was digitized from more recent aerial imagery as indicated by the black line on this geologic map on the right. The results of the non-normalized model show that the red areas on this figure show high predictability for karst features. The green areas on this figure show areas of low karst feature predictability. The white areas on this figure indicated by the roads are due to the distance to roads function being divided by 0, which creates a no data field within the figure. Introducing the normalized and weighted model. This model was weighted where the geologic contact was given the most weight out of all of the variables used. This model is more realistic in nature than the non-normalized model previously created. With this model, normalization was conducted. This is where this was placed on a scale from 1 to 10 in terms of karst feature likelihood. Sabin's ratio was also created during this model. This ratio takes aster imagery bands and combines them in specific ratios to show mineral occurrences. This ratio was calculated according to the methods outlined by Arzif et al. 2019. The equation for Sabin's ratio is located by the laser pointer. The output of Sabin's ratio is this map on the right showing locations of gypsum and not gypsum within the study area. When the normalized and weighted model was created, the variables were normalized on a scale from 1 to 10. To make a more realistic model, certain variables were eliminated or weighted more accurately to predict karst features. The variables were weighted as follows: around 34.5% geologic contact, around 27% aster-Sabin's ratio geology, around 17% elevation, around 10% aspect, around 7% slope, and around 3.5% NDVI. These weights were determined by user optimization. The results of the normalized and weighted model, as indicated by this figure on the right, show the areas in red, which is where karst has the highest probability of being present, and areas in green, which is where karst has the lowest probability of being present. Looking at comparing the two models, the non-normalized model, the variables are all similarly weighted. Looking at the normalized and weighted model takes the variables and weights them in a more realistic extent. Looking at the model agreement between the two models, the areas in red indicated in this figure show where both models agree that there is a karst feature present. The yellow, as shown in this figure, is where one model agrees that there is a karst feature present and the other model does not. The areas in white show where neither model agrees that there is a karst feature present. Field verification was conducted over a weekend in November 2019. The maps were created and loaded into a digital application called Avenza Maps, which was put on handheld devices, phones and tablets, that were used to find features on the landscape. 50 points were chosen that intersected the sync fill features that intersected the model agreement. Additional points were documented when visiting high predictive zones that were not associated with sync fill features. 50 points were visited, as shown in the red on this figure on the right. 26 points were verified during the field verification, which is shown with the green dots on this figure. That's a 52% accuracy. 12 additional points were found during this field verification, as shown in yellow. Looking at the northwestern corner of this property, there's a surface geology issue. It was determined that the aerial mapping method used by the Kansas Geological Survey did not adequately map the geologic units in this area. Looking at the karst feature relationship to NDVI, based on the range of NDVI values around karst features, it was determined that the NDVI range is very small and near the value of 0.01 to 0.02. The very small range in NDVI around karst features suggests that karst develops in a stable growth condition regardless of climate. These models can be applied to vulnerability. Infrastructure can be very vulnerable to karst features. You can have sinkhole collapse, structural damage, livestock loss, as well as aquifer contamination. This was created by reclassing the land use and adding it to the agreement model output previously stated. Looking at the vulnerability map to infrastructure, as shown in the photo on the right, the red shows the highest vulnerability to infrastructure, and the green areas show areas of lowest vulnerability to infrastructure. The first hypothesis within this thesis was that a predictive model could be created to identify the location of karst features and would be more accurate than the sync fill function within ArcMap. This hypothesis was proven correct. Looking at the second hypothesis, a higher amount of vegetation density according to NDVI signifies a greater amount of karst features present. This hypothesis was proven false. Instead, karst features appear to form within a relatively uniform NDVI range around karst features near the value of 0. Samples were collected for petrographic analysis during this research. Samples were collected from cave ledges, as shown in the top photograph, as well as outcrops and sinkholes, as shown in the bottom photograph. 25 petrographic thin sections were created, and these thin sections were created according to methods outlined by Hutchison in 1974. A 100-point point count was conducted with these thin sections. A graduated stage was used to move the thin section in a constant motion and to improve the accuracy of the point count. The categories of the point count analysis were gypsum, dolomite, pore space, and extra space, such as fractures if they were seen in thin section. These are some examples of thin sections seen within this study area. This thin section on the left shows gypsum as indicated by the arrow as seen in thin section. This is in cross-polarized light. And this thin section on the right shows pellets and ooids as seen in petrographic thin section. And this is in plain polarized light. Looking at the results of the point count, 2 sedimentary facies were discerned from the results of this point count. The first facies is the algal mat facies, which is defined as bands of altering algal layers between dolomite and is shown in this photograph on the top. The second facies is the poloidal facies, which is shown in this bottom photograph and is defined by pellets and ooids in petrographic thin section. This table on the left shows the sample locations and the representative facies that were identified with that location. Looking at the elevation ranges of these facies, the poloidal facies has an elevation range from around 560 to around 570 meters in elevation. The algal mat facies has an elevation range from around 559 to around 564 meters in elevation. This signifies that the algal mat facies is below the poloidal facies, looking at the stratigraphic succession within the property. This table on the left shows the elevation ranges with their respective facies. The facies, we're looking at the facies distribution on the study property. The algal mat facies and poloidal facies were plotted as shown in this map on the right. The facies overlap one another in some locations, as indicated by this red oval on the property area. The third hypothesis within this thesis was that a single petrographically uniform layer controls karst feature formation on the property. This hypothesis was proven false. Instead, it appears that there are at least 2 units that contribute to karst feature formation on this property, or there's an extremely heterogeneous layer present. Within the summary, the combined model approach was more correct in identifying the location of karst features compared to the sink fill function within ArcMap. These models are very useful for vulnerability mapping on the study property. The range of NDVI values for karst features is a narrow range near the value of 0. 2 sedimentary facies were discerned from the petrographic thin sections that were collected within this study area. The 2 facies signify that there are 2 karst forming layers in the property area compared to a single layer proposed by previous researchers. Looking at limitations in future work, better resolution imagery and LiDAR data could be purchased to aid in the karst feature detection and field validation within this study property. You could also expand the model to other Permian Plain formation areas within Kansas, such as Comanche County to the west of Barber County. Detailed mapping could also be conducted within the northwestern portion of the property as previously shown due to the superficial geology issue. Higher resolution of petrographic samples could be collected and from more areas to better constrain the detailed stratigraphy of the property and map out facies relationships that may result. Some acknowledgements. I'd like to thank my advisor, Dr. Jonathan Sumrall. I'd like to thank my committee members, Dr. Keith Bremer and Dr. Richard Lishashenko. I'd like to thank the property owners, Mr. and Mrs. Hinz, for their cooperation. Without their cooperation, I would have been unable to conduct this research. I'd like to thank Dr. Jay Sims for selecting me to receive the 2019 South Central GSA Student Travel Grant, which has helped me present this research at the 2019 Geological Society of America meeting in Phoenix, Arizona this past fall. A special thank you, I'd like to thank geoscience graduate students, Jonathan Camello and Alex Lyles, for their assistance with this fieldwork and sample collection during this thesis. I'd also like to thank a special thank you to Caitlin Gavi for her assistance with fieldwork, data collection, and the creation of the petrographic thin sections. Here's my literature cited. Questions?